This is base Factorial, aka Factoradix, Factoradix, Factoradix. This is a stupid word. These are two names for the same thing. The name I came up with for it is Factorimal. Most of the time, people write Factorimal with normal looking digits. Not me though. I write it with each digit converted to Factorimal, allowing for all infinity positive integers to be represented with just 4 different symbols. Although I'm not the first to even do that. Anyway, somebody in the comments said, I think 0 and 1 should be replaced with digits unique to this notation, as it just feels like a more complicated binary rather than a cool factorial system. So I'm gonna change them to Z for 0 and O for 1. Yep, O is now 1, not 0. Deal with it. I was originally gonna use X for 0, but I'm saving X for something much bigger. I also made another notation for Factorial, but that's for another video. Now we're gonna try addition in Factorial. Let's start small with 9 plus 10. Obviously we can't add them in decimal and then convert it to Factorial. That's cheating. We always start at the ones place and then go left. 1 plus 0 equals 1. Then 1 plus 2 equals 3. Then 1 plus 1 equals 2. Easy, right? Wrong, because this 3 isn't supposed to be here. We were supposed to carry the 1 earlier. It's okay, we can take care of that now, I guess. This 3 is in the 2's place, so we subtract 3 from it and add 1 to the 3's place. Now we have a correct number. This should equal 21. Oh, right. 9 plus 10 is 19, not 21. Let's move on to bigger numbers, like 589 and 692. I chose these numbers to demonstrate carrying the 1 in different places. The rule is, if a number greater than or equal to e plus 1 ends up in the e's place, subtract e plus 1 from it and add 1 to the place to the left. Adding 0 to a number does absolutely nothing, so we know that the number ends in 1, 1. 2 plus 3 gives us 5. This is in the 3's place, so we subtract 4 and carry the 1. 1 plus 4 plus 3 equals 8. This is in the 4's place, so we subtract 5 and carry the 1. 1 plus 4 plus 5 outputs 10. This is in the 5's place, so we subtract 6 and carry the 1. Then we immediately drop the 1 right into the 6's place. And as you'd expect, this gives us the number 1281. Now let's try subtracting two numbers, like 614 and 473. Subtraction is just addition in reverse. If the e's place digit of the top number is lower than the e's place digit of the bottom number, a 1 is taken from the digit to the left in the top number, which becomes an e plus 1 that gets added back, just like subtraction in decimal. 0 is lower than 1, so it borrows a 1 from the 2's place. 2 minus 1 is 1. 0 is less than 2, so we take a 1 from the 3's place. 3 minus 2 is 1. 1 is smaller than 2, so we take a 1 from the... Nope, can't do that. The 4's place is empty. A 1 has to be taken from the 5's place first, and then we can take from the 4's place. 5 minus 2 is 3, then 4 minus 4 is 0, then 4 minus 3 is 1. This gives us the answer of 141 as expected. Next, we will do multiplication. Addition and subtraction are a little more complicated in Factorial than decimal. Don't worry though, as multiplication is a lot more complicated. In decimal, multiplying by 10 is baby easy. Just move all the digits to the left. However, in Factorial, multiplying by any number takes effort, and here's why. If you multiply 2 powers of 10, the output is another power of 10. But if we do the same for factorials, the answers aren't so nice. For example, 6 factorial times 3 factorial is 2 times 3 times 4 times 5 times 6 times 2 times 3, not 2 times 3 times 4 times 5 times 6 times 7 times 8. As a result, not only do we want basic small numbers on a multiplication table, we also want their factorials. Let's do our first multiplication problem. 34 times 61. We're going to break it up into smaller rectangles. The rectangles in the one row are obvious answers, and the sum of the row is just 34 again. The other rectangles are factored and remultiplied. Then we do more multiplication. Math only leads to more math. In the end, we have to add all of these up. Eventually, we get our answer of 2074. But is it really worth doing a cajillion multiplication problems in one? Thank you so much for watching! Let me know what you want me to talk about next.